Hey everybody, so today we're going to start looking at different patterns within numbers, and more specifically, how do we classify them? How can we predict them? How can we write them as expressions? But today we're just going to look a little more general in terms of what is a sequence, and then some different terminology that we'll need to know as we go through. So first off, what is a sequence? A sequence is basically just a list. It can be numbers, it can be variables, nothing specific. There can be a pattern to it. So I'm going to zoom in here a little bit. So I could say I've got the pattern 2, 4, 6, 8. This could be a sequence. There could be no pattern to it. I could do 1, 7, 2, 6, whatever. I could have a finite sequence. This first sequence would be finite because I stopped it after 8. If I want to take my second sequence and make it infinite, infinite, all I'll have to do is put a dot, dot, dot after. So if we see that dot, 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 we know it's an infinite sequence. If we don't see that, then we can say that that is a finite sequence that has 4 terms in it. So let's go ahead. I want to go ahead and define some terminology that we'll be using. So when we talk about a sequence, you're going to see the letter A lot, basically just meaning sequence or term. And then every A will have a subscript, typically an N. An N represents the number of term in the sequence. So for that first sequence that I wrote, 2, 4, 6, 8, I would say A1 is 2 because that's term 1, and then it goes to term 2, term 3, term 4, etc. So it says N equals 1, N equals 2, N equals 3, N equals 4. So if I ask you to find the first 4 terms of a sequence that's been defined as A sub N equals 3N minus 2, that again just means we're going to be using the numbers N equals 1, 2, 3, 4. Those would represent the first terms in my sequence. So if we plug in 1 to our sequence, so that would tell me that A1 is 3 times 1 minus 2, which is 1. So my first term is 1. Second term would be A2, so 3 times 2 minus 2, which would be 4. Third term, A3, would be 3 times 3 minus 2, which is 7. And then A4, last one I'm finding, 3 times 4 minus 2, which is 10. Okay, so again, N we assume starts with the number 1 as term 1. Plug each of those values in for as many as it asks you to do. I'm going to skip over B. We'll come back to that, check some numbers later. Now let's work backwards. So if I give you a sequence, can we define it using an AN? Okay, so what helps me in doing this is to actually number my terms. I'm going to zoom in. I can't zoom in much more. So I'm going to actually number these terms. So this is term 1. So that would be an N value of 1, then an N value of 2, and an N value of 3. So those, I need to figure out how those correlate to the actual term value. Okay, so if N equals 1, it's a half. If N equals 2, it's a fourth. If N equals 3, it's an eighth. What I can see is that all the numerators are staying 1. So I'm going to go ahead and say that AN equals, because that's just term N equals. So 1 is all the numerators. Denominators, it looks like they're multiplying by 2, which is a nice pattern to notice. But how does that relate to the actual term number? It's not like I'm taking the term number times 2. 1 times 2, well, that works. 2 times 2, that works. But 3 times 2 is an 8. So we have to think about how can we use these values of n to get the numbers 2, 4, and 8. Now, because we are multiplying by 2, we can think about it as powers of 2. So if you were to take 2 to the first, or 2 to the second, ooh, it went away, 2 to the second, or 2 to the third, that does match the denominators. So it looks like my denominator for my AN is 1 over 2 to the n, where n again represents the term number. If we plug that term number in, we get the term of the sequence. This is what we call an explicit formula. And by explicit, that just means I can find any term I want to by plugging the value in of n. I can jump to the 100th term and plug in 100. I can find the 32nd term by plugging in 32. So that's what an explicit sequence does, or an explicit formula does. It takes us straight to the value we want to find, because we're going to see something different here in a minute. Let's go ahead and look at letter B. So again, I'm going to label these. I'm going to switch colors so we can see them. So this is my n value. N equals 1, I get 1. N equals 2, I get 3. N equals 3 is 5. N equals 4 is 7. Again, we're trying to find the relationship between our value of n and the term itself to write our explicit formula. I can see here that my values are increasing by 2. So again, that might have something to do with my explicit formula. Relationship between my n value and the term itself. Let's see, if we multiply each of our n values by 2, let's check that. If we multiply by 2, that would be, so I'm going to say 2n, would be 2, 4, 6, 8. Do you see the relationship between that and the term number? And it looks like for each of them, it's that 2n value minus 1. So I'm going to say an for my explicit formula is 2n minus 1. I want to just give you a little warning. Some of you will be good at spotting these patterns and writing them out. Some of you will be not so good and it will take some extra practice. So don't get frustrated if you're not getting it at first. Okay, it just takes practice. We will be learning some more formulas, more patterns that we can use as we do some of these sequences. Some of you just kind of have to recognize. So I'm going to leave you with letter C. We'll come back to it tomorrow, but try your best, see if you can come up with a formula for that one. That one's even a little more different. Yeah. Okay. So we just talked about an explicit sequence in which we can plug in the value of n and find that specific term. Recursive sequence is the opposite. Recursive sequence, I can't just say if n equals 7, I'm going to find the 7th term. A recursive sequence is one in which the terms build on previous terms. In some sequences, we can look at both recursively and explicitly, and we'll look at one of those here in a sec. Some of them we can't, and we cannot define it explicitly. We have to know what's come already to keep going and to define more terms. The most famous example of a recursive sequence is what's called the Fibonacci sequence. And I'm probably going to spell this wrong because I usually do, because I can't remember if there's 2 n's or 1. I'm going to go with 1. Might be wrong. I'll fix it tomorrow if it's not, or if it's not right. Okay, so the Fibonacci sequence starts with the numbers 1 and 1, and then it goes to 2, and then it goes to 3. Okay, so I've started with a little pattern, changed it, then it jumps to 5 and 8. So take a second, pause this, and see if you can come up with a definition, or not even a definition, but the next few terms. Can you figure out what comes after 8? And then what comes after that, and then what comes after that? Can you identify that pattern? So again, pause me for a sec, come up with that, and then I'm going to define this recursively. All right, so if you came up with your pattern, you should have found that the next 3 numbers were 13, 21, and 34. If you didn't come up with the pattern and you're cheating and you're going ahead, you probably have no clue where those numbers came from. But here's the pattern. What the Fibonacci sequence does is it takes 2 terms, it adds them together, and creates the next one. And then it takes the next 2 terms, adds those together to create the next. And then so on and so forth. So 1 plus 1 makes 2, 1 plus 2 makes 3, 2 plus 3 makes 5, 3 plus 5 makes 8, etc., etc. So could I ask you to write down the 20th term? Well, no, because to know the 20th term, you would have to know the 19th and the 18th. But to know the 19th, you'd have to know the 18th and the 17th, etc., etc. So this is a sequence in which we cannot define it explicitly. I can't go straight to a specific term. I've got to define it built on those previous terms. A lot of times when we define a recursive sequence, we use the subscript k. So I'm going to say that AK, so any term in the sequence, is built on the term before. So what comes before k? And I know alphabetically it's j, but when we're talking about sequences, it's just k minus 1. So term k is term k minus 1 plus the term before that. So what would come before k minus 1? That would be k minus 2. So this is a recursive definition for the Fibonacci sequence. Any term is the term before it plus 2 terms before it. Okay, again, we can't do it explicitly, we can do it recursively. So let's try a recursive formula. So I would like to find A3, so the third term in my sequence, if 3 times A, k minus 1, again, this just means what came one term ago, plus 4. So basically, to find A3, I need 3 times A2, so the term before it, plus 4. But that assumes that I know what term 2 is, and I don't. So here's what I did. I didn't give you enough information. Okay, I did this on purpose. I did not make a mistake. But you have to have some previous knowledge. We can't go straight to a recursive formula without any terms given. So let's say this. Let's say that A1 is 5, just for kicks. Okay, so if I want to find A3, I know A1. Well, if I know A1 is 5, then I'm going to use that to find A2. And A2, or any term, is defined as 3 times the term before it. Well, the term before it I just told you was 5, plus 4. So 3 times 5 plus 4 must be, or is, 19. So that must be term 2. And now I can use that to find term 3. So A3 would be 3 times the value before it, that was 19, plus 4. And 3 times 19 is 57. 57 plus 4 is 61. So that tells me that A3 is 61. But again, because it's recursive, I had to build up to get there. I couldn't go straight to term 3. So that's the difference between explicit and recursive. Explicit, I can go straight to where I want, whereas recursive, I've got to build. This next idea is a factorial, which is something we have talked about in a couple different ways or a couple different times. So just a quick review. Factorial is just the exclamation point, which is the mathematical definition of which is to take that value with the factorial and multiply it by all the numbers that came before it. So notice I'm just saying n minus 1, n minus 2, etc., until we get down to the number 1. So 3 factorial would be 3 times 2 times 1, which is 6, right? Or 10 factorial would be 10 times 9 times 8 times 7, blah, 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 until I get to 3 times 2 times 1. And I have no idea what that is. So factorials we're going to see used in sequences in some different definitions. We've already seen them with our binomial theorem, so that shouldn't be a surprise to you. So if we just look at 6 factorial divided by 4 factorial, I would suggest we write out some terms. So 6 factorial would be 6 times 5 times 4 times 3 times 2 times 1. 4 factorial is 4 times 3 times 2 times 1. The nice thing about this is we've got a lot of stuff that cancels out. Both the numerator and denominator have that 4, 3, 2, 1 that will cancel out. So 6 factorial divided by 4 factorial is really just 6 times 5, which equals 30. So I'm going to leave you letter B, but think about it the same way. Write out some terms, and then think about what will cancel out. Okay? Okay, last thing that we're going to finish up with is sigma notation. So we've been talking about sequences as a list of terms, and sometimes showing some patterns, sometimes not. Sigma notation is when we are going to take those lists or those sequences and actually find the sum of them. What happens when we add all these up? Sigma is the Greek letter. It looks like the big E. So you're going to see that. That's an uppercase sigma. Did you know the Greek letters have uppercase and lowercase? Now you do. And when you see it, it literally means add. Below the sigma, you will have your variable defined with a starting value. I'm just going to say 1. Doesn't have to be 1. It can be n equals anything. Above it will be an ending value for your variable. So if I see something like this, that means I'm going to start by plugging in the number 1. And then I'm going to plug in the number 2 and 3 and 4 and 5. And I'm going to keep plugging in numbers until I get to the number 10. This is the last value that we will plug into our formula. Okay, so that's the basic sigma notation. And then off to the right, you'll have some expression to plug it into. Maybe it's like n plus 1. So this would indicate that I'm going to start by plugging in the number 1. So 1 plus 1. Then I'm going to plug in the number 2. And then I'm going to plug in the number 3, etc. And I'm going to keep going until I hit the number 10. And 10 is the last thing that I plug in for my variable. So I have that whole list of numbers stopping at 11. And then we add them up and we get our answer. Okay, so when it says find each value, and I've got the in sigma notation, n equals 1 to 10. I don't know why I chose 1 to 10. Oh well. Of 6n plus 1. Again, I'm going to start by plugging in the number 1 to find my first term. So my first term is 6 times, of course I arrowed it to the 6, 6 times 1 plus 1, which would be 7. And then I'm going to plug in the number 2. So 6 times 2 plus 1 is 13. And 6 times 3 plus 1 is 19. And 6 times 4 plus 1, etc., etc. I'm going to keep going. And then the last number I'm going to plug in is the number 10. So 6 times 10 plus 1, which is 61. So our final sum, and I don't have a calculator, I'm not going to add it up, is whatever the total of this series is. So once we get to adding things, we actually call it a series. Okay, so I'll let you all add that together. And then looking at this next one again, I'm not going to do it, but do you see how I've changed this next problem? I'm not starting at 1 anymore. Oh, I have an error here. I'm starting at 3. So this tells me that my first value I'm plugging in is 3 for the n. So this should be n because that should match your variable. So first we would plug in 3, and then we'd plug in 4, and then we'd plug in 5, and we would keep plugging in numbers until we get to 8, which is the last value we would plug in. And that would give us our final sum. All right, so again, I will leave that to you to do and check tomorrow. So that is your introduction to sequences, a little bit of series, a little bit of notation and definition. We will practice that a little bit tomorrow, and then we will continue working on specific types of sequences and series.